a bit of a hybrid class. We will have the first half. I'll talk about policy grading. We started policy grading, but we'll cover the rest of policy grading, show you some cool videos, and then we will have group R2D2 present lazy SP. Right. So it's a planning algorithm, but we didn't get time last week, so we'll do that. Okay, so where are we in our journey? We have covered imitation learning and told you that it's garbage. And now we're going to do policy grading. And so policy grading is a technique for reinforcement learning, and it's the simplest possible way to do reinforcement learning, right? So let's start with some logistics and we'll get into the math of policy grading. So one paper presentation today. Guest lecture 1 is on March 1st from the folks at TRI. And guest lecture 2 is on March 4th, so on Monday, from Vikas Kumar, who is adjunct at CMU. He does really cool work. And so we'll host them here. So if you want to come here, you're welcome to. If you want to stay at home, you're welcome to do that. Either way. And we'll release the final project today. Yeah, we'll release the final project either today or early tomorrow, so that you can do it for the rest of your 2 weeks. Okay, so that's some logistics. Any other questions, concerns, things we should discuss? Okay, great. So we want to study policy grid, so we'll discuss policy grid. We'll talk about how to improve policy grid. So like what are some issues with policy grid and how can we resolve them, right? So we discussed there's multiple ways to approach this decision-making problem. We discussed imitation learning. We're going to complete model-free reinforcement learning through policy grids, and next class we'll cover model-based reinforcement. So the idea behind model-free reinforcement learning is to take this objective, which is essentially maximizing the sum of expected rewards. That we want to find a policy which maximizes the sum of expected rewards, and by the definition of expectation, this is just the integral of p theta tau, which is the probability of a trajectory, times r tau, which is the return of a trajectory. And so this is the expected return of a trajectory. And you want to find the policy which has the highest expected return. And so the idea behind policy gradient is to do it to the dumbest possible thing, which is gradient descent, right? So we're going to take our objective and we just want to do gradient descent. And what we discussed last time is why this is not so simple, right? So can someone remind me why just doing gradient descent on this objective is not trivial? Like we do gradient descent all the time, right? All of deep learning is gradient descent for gradient descent. Like why is this any different? Yeah. Okay. You're doing gradient on the thing you're taking the expectation with respect to, right? So you're doing a gradient on p theta x, so you're taking the expectation with respect to p theta x, not the thing inside the expectation, right? So it's supervised learning, and in every type of machine learning that is like seen in vision and language, not every type, but many types, you're typically doing gradients of the thing inside the expectation, and the expectation is under a stationary data set, right? You collect the data set, you do supervised learning. In policy gradient or reinforcement learning, your data distribution is dependent on the policy. So the intuitive way to think about it is in supervised learning, someone goes and collects a bunch of data for you, and then you try to like minimize the loss function of that data. In reinforcement learning, you are collecting the data yourself, and you're being evaluated on whether your data is good or not. Right? And so the gradient is on the thing that is collecting the data, not on the loss function on already collected data. Does that make sense? Right. So this, like when you have a gradient like this, right? Because the x sample from g of x does not depend on theta, you just push the theta all the way inside, and you just take the expectation of grad theta f theta x. Right? You just put the gradient all the way inside the expectation, and you just take the expected gradient. So this is what stochastic gradient descent does. It takes gradients on a bunch of different points and averages them. But in reinforce or in policy gradient, you have to do a little bit of different math to deal with this expectation with respect to theta. Right? It is gradient with respect to theta. So that's what makes it different, and we're going to try and work out them, right? So, So we're gonna start from here, and we've said that j theta, which we're going to call our expected return, right, is going to be the expectation. going to be the expectation with respect to trajectories drawn from p theta tau of r tau. Right? This is the likelihood of a trajectory under your particular policy. This is the reward of a trajectory, right? And so let's like write these two things out. This is essentially going to be the product of the first state of a trajectory times the product of the first action times the first state times the first action times the next state times the next action times the next state, the next action, and so on. Yeah. And so this is going to go all the way till P, A capital T given S capital T. Okay. So this is saying that this is the likelihood that you sample the trajectory under your policy. So the theta is going to appear here. This P is going to be pi theta. This is the likelihood when you have a policy pi theta. This is the likelihood that your policy pi theta sample your action, right? And it's not just a product of the action likelihoods. It also depends on how your states transition, right? So the likelihood of a trajectory is a sequence of states, actions, and rewards. It's going to be likelihood of the initial state times the likelihood of the first action times the likelihood of transitioning to the next state times the likelihood of the second action, and so on. Right? That is the likelihood of a trajectory. So this is like how probabilistically likely is it that you sample this trajectories when your policy was pi theta. Yeah. So pi theta is a probability distribution of actions given states. This is your dynamics of your environment, with how the world transitions, right? And you're going to take the product of all of these to give you p theta. Does that make sense? Okay, and what is R tau? You have a question?
Yeah. So we're seeing the
Reward is determined. Okay. Good for it. Okay, so what is R tau going to be? Yeah, so but it's not quite reward, it's return, right? The sum of it. So this is just going to be the sum of our SCAT. That's it, right? So that's the definition of this, that's the definition of this. And by the definition of the integral of the expectation is just the integral p theta tau times r tau times theta. Yes, that's just the definition of a expectation. And so the expectation with respect to p of x of some f of x is the integral p of x f of x dx. The definition, right? Everyone with me so far? Okay. So now you're going to work out the next set of steps without me, right? So you're going to dictate to me what the next set of steps are going to be. So this is what J theta is going to be. We want to do the policy gradient, right? So what we want to do is we want to write out the gradient of this with respect to theta. Yes? Okay, now someone tell me what the next step is going to be. Yeah. Gradient inside the integral, right? So you have gradient theta of b theta tau r tau d tau. First step is gradient goes inside the integral. Okay? You can do that when your system is continuous. And so you're going to have grad theta b theta tau r tau d tau. Now notice I did something deliberate here, which is I didn't take the gradient of r with respect to theta, because the only thing that really depends on theta here is b theta tau, not r tau. So this is going to be gradient, this is going to be r tau. So this seems great. Why can't I just evaluate this? What makes this hard to compute by itself? You might not have a closed form, exactly, right? So you don't have a closed form because you don't know like exactly the form of p theta and so on. The integral might be hard to evaluate for your own functions. And so, okay, so there's no closed form. So what are the other tricks we have learned over the quarters that might help us? Like, what is a different way of evaluating an integral if we don't have closed form? So we have an integral over some stuff. Like think back to particle filtering. Yeah, go ahead. Expectation, exactly, right? So if I could express this as an expectation, then you can evaluate an integral by taking a bunch of samples and averaging them, right? So if you remember the particle filter, we represented things by a bunch of particles, right? And then you could compute expectations by averaging things over the particles, right? The same idea. If I can rewrite this thing, which is not an expectation, right? So if you remember what I just said, the definition of an expectation is the following, right? If you have an expectation, it's equal to the integral dx fx dx, where there's a probability and the thing that you're doing expectation with respect to. And so, or this thing you're doing expectation of, sorry. So this thing is not an integral, right? Because I don't have any p theta, I only have gradient p theta, right? It's kind of a pain in the ass. I don't do it. So how can I convert this thing into an expectation? Multiply and divide. Perfect. So you multiply and divide by p theta tau and p theta tau. You have grad theta p theta tau, r tau, p theta. So we didn't change the expression, we just multiplied and divided by p theta tau. And now the trick we're going to use is what? So I want to write this as an expectation. What's the trick that I use? Make it into a log. So the trick we're going to use is that grad theta log p theta x is going to be equal to 1 over p theta x times grad theta p theta x. This is by chain rule, the chain rule of differentiation. And so if you have basically log x, you take the gradient with respect to x is equal to 1 over x. That's the definition of the log derivative. And you're just going to use the chain rule here, right? So you can write this as the gradient with respect to p theta of x of log p theta of x times the gradient of p theta of x with respect to x, right? That's just chain rule. Make sense? So whenever you have multivariable, whenever you have like a function dependence, you can say log p theta of x with respect to theta is gradient of this with respect to intermediate variable and the gradient of the intermediate variable with respect. That's the chain. And so, everyone with me on the chain rule? Yes? Okay. So now the nice thing about this whole shebang is that you can now say that this expression over here looks pretty similar to this expression over here. Right? They're like kind of the same, which means that you can rewrite this integral as p theta tau times grad theta log p theta tau times r tau times p tau. Yeah. And now this is an expectation, right? Because you have p theta times some f, right? Integral of that. So now you can rewrite this thing, like look at the definition of this, look at the definition of this. Right? You can think of this whole thing as f, this whole thing as p. Right? Just do pattern matching. Okay, so now you can rewrite this whole thing as the expectation of p theta tau of grad theta log p theta tau times r tau. Beautiful. Right? So now what we've done is we've converted the gradient of our expected rewards into an expected gradient. Right? And this is like a really common trick in reinforcement learning and black box optimization, things like that. But it's basically multiply and divide and use the chain rule to replace this result. And so essentially what it's saying is that the gradient with respect to theta is the expectation with respect to p theta tau of grad theta log p theta tau times r tau. Right? And let me first get rid of my messy handwriting so we can write out the whole expression here, right? So the gradient with respect to gradient of j theta is expectation of p theta, grad theta log p theta tau times r tau. Right? And so intuitively what this means is that it's essentially formalizing the notion of trial and error. So it's saying that you're going to sample a bunch of trajectories from your current policy, and then you're going to increase the likelihood of them proportional to the reward. So things that have higher reward, you increase or higher sum of rewards, you increase their likelihood more. Things that have lower sum of rewards, you increase their likelihood. And so essentially it's saying that if you remember how supervised learning works, right? It's just like weighted supervised learning. You're sampling a bunch of stuff, and then you're weighting how much to increase the likelihood of something based on how good it is, right? So it's like trial and error, try a bunch of stuff. I do the good stuff more and the bad stuff less. That's the whole intuition. Does it make sense? Any questions? So this is not something we can implement on in code yet. So we'll try to like reduce this, and I'll try to make it into something actionable. But at an intuitive level, does this make sense? So let's try and like write this out in terms of something that we can actually write down in terms of code, right? So we know that the likelihood of a trajectory is the likelihood of the initial state times the likelihood of the dynamics times the likelihood of the policy. That's the thing that we wrote in the last slide. So likelihood of trajectory is all of that. And then if you take the log of the likelihood of a trajectory, right, you just take the log of a product of a bunch of terms, it's just the sum of each of those, sum of the log of each of those terms. Right? So you can say that log of this whole thing is log PS naught plus the sum of log dynamics plus the sum of log policy. Right? Just take the log of that thing, you know, the product of log is a log of products is sum of logs. Right? And so what we've done is we've converted log probability into this sum. And that now we're going to note something pretty nice, which is that if I take the gradient of each of these terms with respect to the theta, which is the policy parameters, right? That you can write this as the gradient of the initial state with respect to theta, plus the gradient of the dynamics with respect to theta, plus the gradient of the policy with respect to theta. Right? So like, which of these actually depend on theta? Only the last term, right? The last term is the only thing that depends on theta, is the parameters of the policy, right? The only thing that depends on theta is the last term. This term and this term do not depend on theta, right? So if something does not depend on something else, then what is its gradient? 0, right? So 0, 0. So you can just say that the grad log e theta is just the sum of grad log phi at given s. Right? So it's just the gradient of the policy, the gradient of the dynamics, the gradient of the initial state cancel out. And this is why it's called model free, because the model does not appear anywhere, right? So the model is not necessary, and that's why it's called gradient free, right? Or sorry, model free. So this is called model free reinforcement learning because the model cancels out with the gradients are 0. And so you can write grad theta log p theta tau as the sum of grad log phi at given s. Right? And so what does this mean? Imagine that you had a neural net, right? It takes an ST, gives you 80, right? And then you have like a log phi 80 given ST. To get this gradient, you can just use PyTorch to get gradients back to this neural network, right? So essentially what you're doing is you're saying you just take the sum of these gradients back through the neural network, and you don't need to worry about the dynamics, you don't need to worry about anything else. Phi is something that's completely under your control. Like the policy, it's the rule that you decide to go from state to act. Okay. So that's the basic idea behind policy gradient. Now let's plug those things together, right? So if we go back to our objective for the gradient, right? It's expectation under p theta tau of grad theta log p theta tau times the sum of reward. Right? That's the thing we worked out 2 slides ago. Like that's the thing we worked out right here. It's expectation p theta tau times grad theta log p theta tau times r tau, right? Now if you like substitute in our expression from the previous slide, right? In the previous slide, we figured out that grad theta log p theta tau is just the sum of grad theta log phi, right? You substitute that back in, and you see that this just becomes the sum from t equal to 0 to t of grad theta log phi theta at given st times the sum of reward from 0 to t of r st. Yeah. So the way that you implement this in practice is you just like sample a bunch of trajectories of the environment, and then you score each of them by their sum of rewards, and then you increase the likelihood of the action in every trajectory by the sum of rewards in that trajectory. Right? And so let me see if I can show you an intuitive figure. Right, so imagine that you had like 2 trajectories, one which is good, one which is bad, right? You're going to let's say you have 3 trajectories, one which is 100, reward one, which is 30, reward one, which is minus 10, sum of rewards. You're going to try and increase the likelihood of all the actions in this trajectory and decrease the likelihood of the action in this trajectory and increase the likelihood of the action in this trajectory only by a little bit. Right? And so essentially, this is exactly the same notion of trial and error. You're going to sample a bunch of stuff, and then you're going to upweigh the stuff proportional to its sum of the weights. Does that make sense? So, that expectation you can replace with a bunch of samples. So you sample a bunch of trajectories, you weight every trajectory by its sum of rewards, and then you increase the likelihood of actions in that trajectory by the sum of rewards. Okay, so that's the intuition. So the resulting algorithm is called reinforced or vanilla policy gradient. Basically looks like this. You're going to sample a bunch of trajectories from the policy by running it on the robot, running it in the simulator, whatever you want. They're going to compute the gradient by taking the grad log phi, multiplying it by the sum of rewards, and then you're just going to do gradient descent on the parameters of the policy. You're going to repeat, right? And so you're going to like sample, compute the gradient, add the gradient, sample from the new policy after the gradients have been set, or after the parameters have been updated. And so this scheme is called on policy because you're going to use the latest batch of data that you collect from your policy to construct your gradient update. And some of the other methods we'll discuss are going to be off policy because they don't need to just use your latest batch of data, they can also use previous data. Right, so it's on policy because you sample a bunch of stuff, use that stuff to construct the gradient update, and you take the update and you have to sample again. Right, so to go in this loop. And this is essentially the simplest notion of trial and error that reinforcement learning promises. It's saying, try some stuff, increase the good stuff, decrease the bad stuff, move your policy, repeat. That's it. Yeah, we're looking. Any questions? Concerns about the policy grid? Yeah.
You said gradient descent.
Yeah. It's just the opposite of gradient descent. Because you're trying to maximize the reward.
Oh.
Yeah. So like typically gradient descent, you're trying to minimize loss, you're trying to maximize reward. You could also think about minimizing negative reward. You can do the same. It's kind of the same objective. Okay. So I have some pseudocode in here for anyone who's interested. The pseudocode is like super duper simple, like 10 lines of code. I'm going to skip over it for the sake of time, but essentially, the main points I wanted to make are that in continuous policy gradient, you're going to use Gaussian likelihoods, and in discrete policy gradient, you're going to use softmax with cross entropy. Okay? And so I'll refer you guys to the slides to look over these in more detail, but let's keep going to try and understand this more intuitively. So we covered imitation learning, then we covered behavior cloning. Behavior cloning looks something like this. You want to sample X and Y from your data set and increase the likelihood of producing Y when your input is X. Okay? And so you want X is going to be your states, Y is going to be your actions, and supervised learning is saying try to find a policy that increases the likelihood of optimal actions and optimal states. Okay? And so this is supervised learning. You can compute this by doing this like average over grad log fees. The difference in reinforcement learning is that you're going to compute grad log phi's, sum it up, weighted by rewards, and then you're going to keep recollecting the data, right? So as opposed to supervised learning, where this data is stationary, right? In reinforcement learning, your data is also going to change. And so the reason it's not just supervised learning is because you have to decide what data is good so that you can collect data the next time, right? And so that's what makes reinforcement learning different from supervised. And as a result, it doesn't suffer from the same types of like compounding error problems because you're accounting for how the data will be. Right? So that's policy gradient. I will take maybe 5 more minutes and then we can move to the next. So the main issue with policy gradient is that if you think about this, it's saying take the grad log phi, take the likelihood at a particular state ST and action AT, and increase it according to the sum of rewards in the future, right? And fast actually. So sum of rewards in the whole trajectory will decide how much you increase the likelihood. Now the problem is it doesn't tell you how good a particular action is every action is coupled with everything else in the whole trajectory. And so imagine that I took one thing that was good and then did a bunch of bad stuff. What's going to happen is the reward is going to be pretty low, even though what I did was good. Right? Whereas if I like did one bad thing and then did some good stuff after, even if that thing was bad, like it would be treated as good because it's coupled with a bunch of other good stuff. Right? And so the problem is that you have this, it's a problem called variance, right? So it's basically saying that because the goodness of a particular action at a state is coupled with all of the other states and actions in the future, you need to get a lot of samples to disentangle whether something is good or not. Right? So basically you have to like, imagine you're taking one action, you have to try that with all of the other stuff in the future to disentangle whether it's like fundamentally a good thing or not. Right? And so this is essentially what we call a single sample estimate, which says that you've taken a trajectory and you're just going to take the sum of rewards in that single trajectory and weight things by that. But you could get lucky there, you could get unlucky there, right? And so you have a high variance estimate because you're just taking what happened in the future of your trajectory, and you're not considering all the possible futures that could be. Right? And so really what you want is something that looks more like this, which says, okay, I was here, I took an action, let me consider all the possible futures that could be, and that will tell me how good or bad an action is at a state. But instead, what we have is a one trajectory, and you could get lucky, you could get unlucky. And so the problem then is that you have high variance, depending on whether you got lucky or unlucky, your gradient is very different. Right? So imagine you got unlucky, the future states were unlucky, then you're going to have like a way lower reward. And if you're lucky, then it's going to way higher reward. Right? Whereas if I like took an average over many possible futures, then you wouldn't have this problem. Right? And so this is an issue called variance in policy gradient, and that's kind of what makes these policy gradient algorithms so inefficient. Because if you need to really reduce the variance, one way to do it is increase the number of sample steps, right, by 1,000x. And so if you look at any implementation of PPO or PRPO or policy gradient, all of them have huge batch sizes because they need to reduce the variance. Right? So they need to deal with these unlucky events. And so that's the main issue with policy gradient, right? And so I won't have enough time to cover the other things in detail, but essentially all of the improvements on policy gradient are essentially trying to reduce the variance, which means they're trying to like deal with the fact that an action is coupled with all the things in the future. You only have a single sample estimate, and so they all try to approximate some version of like computing an approximate value of a state by averaging many. Right? So we will skip those for now, but let's go look at some examples of policy gradient in action, right? So here's an example from one of my lab mates, John Philbin, back in 2016. But he was trying to get this humanoid to walk, and he's just using policy gradient algorithms. And you can see that it gets better after 1,000 iterations. It's learning to walk, it's learning to stand up, etc. Just trying to maximize reward. And so at the time, this was amazing. We're in a different time now, but it's good then. This is also used for a bunch of examples on Dota. And so some of the best examples on Dota, I think StarCraft is a little different, but on Dota definitely it was PPO and some version of like policy gradient that was used to achieve superhuman levels. And then we have some examples on things like robotic cubes and so on. So these are mostly experienced simulation and transferred to the real world. And the reason is that the algorithms here that I talked about are very inefficient. So you can't run them in the real world as if. But you can like get them to do really complex simulations, even they transfer over to the real world. Some more examples here are
we demonstrate
robotics
learning
examples,
to walk
right?
in
So
the
we
wild
have
in under
these
20 minutes
examples
using
are
the
actually learning directly in the real world. So
At
some
the
of these
start,
are
the
from
robot's completely untrained, but it's given the
people
goal
that
of
we know.
picking up this trait. The
And
robot
there's some
explores by
probably
moving its
differently,
legs,
but basically
observing
they're
how its
trying to learn
actions affect
directly in
its
the real
movement.
world.
With
And
this
so the
feedback,
trick
the
is
robot
just
quickly learns
if
how to
you
coordinate its
can
movements into a
reduce the
naturalistic working
variance
state.
on these.
While it makes progress up the hill and encounters new challenges, it's able to learn from its experience and adapt its newfound skill accordingly.
Reduce variance.
Here in just about 10 minutes, the robot is able to walk up the trail. Typically, this learning requires hours worth of data and has been mostly applied in controlled lab settings.
And a bunch of different
To the
tests.
various outdoor terrains where it can train the robot to traverse. where the robot cannot
I think
receive
basically
perfect
if you're
feedback about
careful
its
about
performance
variance
and the terrain is
possibilities, it can be
unstructured
very
and
powerful.
complex.
The main thing you have to worry
In
about
all
is
cases, the
when
robot's
you take
able
an
to learn an
action,
effective gait
you
for
need to
each terrain
evaluate
in
its
under 20
quality
minutes.
without having
Thanks
everything
for
else
watching. For
covered.
details, training videos, and code to
That's
train
what-
your own robot, please visit our project
Does that make
website.
sense? Cool. All right. Well, that's it for me today. And I'll let group R2D2 present. Did you email it to me? Sure. We can, if we can figure out how to do it in presenter mode. So. Presenter view.
Yeah.
That. I don't know why this guy isn't getting bigger, but. Yeah, I think that's fine.
Okay.
Sounds pretty awesome.
Let me make sure Zoomers can see it.
I don't know. I don't know if I'm a kid that shoots. My brother is.
That's you. Can you see this on Zoom? Can someone on Zoom either say something or reply?
Yeah, I can see it.
Yeah, we can see it.
Okay, great. Thank you. Okay, so I think you can go ahead.
Okay, thank you.
Okay. Hi, everyone. So today our group will be presenting on the paper, A Unifying Formalism for Shortest Path Problems with Expensive Edge Evaluations via Lazy Best First Search over Paths with Edge Selectors. So that's sort of a mouthful, but essentially the paper is about the introduction of a groundbreaking approach to optimizing algorithms for shortest path problems. So this paper particularly focuses on scenarios where edge weights or evaluating them significantly dominates the computational runtime. And so hopefully as a review to us all, graphs provide a powerful abstraction that's capable of representing problems in a wide variety of domains. So some examples include computer networking, puzzle solving, and robotic motion planning, which is sort of what we're interested in. And so the computational cost incurred by an algorithm that finds the shortest path can be broadly categorized into 3 different categories. So the first one is queries on the structure of a graph. So for instance, expanding a vertex. In an example that we should be familiar with, like Dijkstra's, expanding a vertex means looking at all of its unvisited neighbors. And so the second source comes from maintaining ordered data structures inside the algorithm itself. So again, from the previous example, maintaining a priority queue. And so the third, but not least, is the computational cost that arises from evaluating these edge weights itself. And so the paper considers like the specific problem domains in which evaluating these edges dominate algorithm runtime. And so this paper focuses on this one research question: how can we minimize the number of edges we need to evaluate to answer shortest path queries? And so this investigation led to 3 primary contributions in the paper. And so the first one is that the authors were able to develop a class of new algorithms for shortest paths. And it's well suited specifically for domains with expensive edge evaluations. The second one is that they were able to show that several algorithms that already exist in literature can be written or expressed as special cases of this algorithm. And they also showed that the extensibility afforded by the algorithm also allows for novel edge selection or novel edge evaluation strategies, which in certain instances can outperform existing algorithms, and they do so in a variety of different test cases. And so for those who don't know, best first search, or BFS, is an informed search algorithm that is commonly used to select vertices for expansion so that these vertices or that these expansions are minimized while also guaranteeing optimality. And so since the goal of the paper is to minimize the number of edges that gets evaluated, the authors use BFS to answer this question of selecting candidate paths in the graph for evaluation. And so the resulting algorithm is called lazy shortest path, or lazy SP for short, and it can be applied to graphs defined implicitly or explicitly. And so this is the pseudocode of lazy SP, and I wrote some definitions on the side, but I'll go more in depth in this slide. So the lazy SP algorithm optimizes the process of finding the shortest path by managing the computation of edge weights. And so it maintains a set E sub eval, and it keeps track of all of the edges whose true weights have already been determined. And so it also has this estimation function, which provides a provisional weight for each element or each edge. And so this function is deliberately designed by the authors to be computationally light. So for instance, it could equate to the geometric length of the edge, or just assign a constant value such as 0. And so to work with these estimates, lazy SP defines a function called lazy weight, and it defaults to the estimated weight for any edge not in the eval set. And so the edge's actual weight is only returned once it's computed and also confirmed. And then the next step is that lazy SP uses this lazy weight function to determine a provisional shortest path by using standard shortest path solver, which operates on the estimated weights. So this step is really nice because it avoids the need to actually calculate the true weights of each of the edges, which can save a significant amount of time. Yes.
Like for instance, in RT and so on, you're kind of defining the edges on the fly, right? And so is this assuming that a graph with connectivity is known and just the edge weights are not known, or what's the assumption? Like, so I guess my point is that in certain cases, you need to build the graph on the fly.
Oh.
Like in RT, you're sampling to build the graph. Does that work here, or does it assume the graph is provided?
I assume that the graph was provided. I didn't read anything about on the fly nodes.
And so if it's okay, so imagine that we sample a bunch of nodes, and then you need to find connectivity between the nodes. Does it earlier what we did is we would take two nodes and do collision checking to see if there's a collision-free path between them, but that's the expensive part, right? And so here, do you just connect everything beforehand, optimistically, and then check it later? What's the
I think that'll get a little bit more in the edge selector function, which I'll talk about right after this slide. But yeah, there are a number of different ways to actually to check which edges and which paths to look at. So yeah, I'll get to that in a sec.
Okay. Yeah, so the candidate path, coming back, the candidate path is deemed to be correct and is returned only if it's entirely composed of edges whose true weights are known. And so otherwise, lazy SP employs an edge selector function, which Jake will talk about, to choose the remaining unevaluated edges in the candidate path to be evaluated. And so the last step is basically using those selected edges, calculating the true weights, and then adding it to the eval set, and then updating the lazy weight function accordingly. And so this process repeats. And so this iterative approach to this algorithm allows lazy SP to efficiently converge to the actual shortest path by strategically minimizing the number of expensive weights and the calculations required. And so I'll pass it on to Jake.
Okay, so when actually going through this algorithm at each step, we need to decide which edges to actually evaluate and run that expensive evaluation function for. And so the paper talks about a number of different approaches. And just on this page is existing kind of approaches for the selector function. So there's forward and reverse are the most straightforward. This is just selecting the first unevaluated edge or the last unevaluated edge. Alternates back and forth. And the thing with these selectors is that they all have some sort of equivalence to an already existing algorithm. So if you use the expand or the forward selector, that's equivalent to lazy weighted A star. So basically, if you use any of the selectors listed on this page, it's not really anything new that this paper proposes. So the actual important part that this paper proposes is the novel edge selectors. So we're free to implement selectors that choose edges in any order. And so the two selectors proposed are weight sampling and partition selector, whose goal is to actually reduce the overall number of edges that need to be evaluated. And so the first one is weight function sampling, and the goal is to just choose edges that are the most likely to be on the truth shortest path. And so the way that it does this is that at each iteration of the algorithm, there is the set of known edges that have been evaluated. And so this algorithm will sample from that set of the known edges and run some shortest path queries between the sampled edges. And that will help determine which edges to actually evaluate next. The problem here, though, with this particular one is that sampling them and running shortest path queries does take quite a lot of time. So that's not, while it does help reduce the overall number of edges evaluated, the actual time to run this is quite significant. So that's why the paper proposed the second selector, a partition function selector, whose goal is the same, but it does it in a little bit of a different way. It uses an exponential path distribution, which is that equation is shown in the bottom left there for selecting the edges. And basically this chooses edges that are, or it assigns a higher probability to edges more likely to be on the path. And it uses that lazy set there, or lazy edge values there, which will either be the like heuristic function for the edge weight if it hasn't been evaluated yet. So yeah, that's the second method, and this method is more of a mathematical approach. And so the authors talked about a lot of optimizations that can be done there for improving time. Like all of the probabilities can be stored in a 2D matrix, and all of the updates in subsequent runs can be done with relatively efficient vector multiplication. So this leads to a lot faster runtime for this particular selector. And that kind of brings me into the actual results and times for running this algorithm. So,
Quick question.
yeah.
So you evaluated some edges, you got their weights or whatever, and then do you like have to replan? So imagine that we had some like W lazy, and then you evaluated, you got W not lazy, right?
Yeah.
And like replan and stuff. Because now my old path that I thought was good is no longer good. Right?
Yeah, I think like if we go back or just overall, the algorithm won't return a path at all until every edge has been evaluated along that path. So it's not, none of them are technically
So
lazy.
let's say we evaluated everything along the path.
Okay.
At some point we realized some path cost was like infinite.
Yeah.
And okay, so now that path is,
Yeah.
does it like, it has to now find a different path, right? So does
Yeah,
it
I
like
mean,
do something clever there, or is it just?
the pseudocode involves using the shortest path algorithm every single time. So in case something like that happens, it will choose a different
Just
path and the
starts
process will begin again. Yeah.
Awesome. So now onto the experiments. They ran experiments across random graphs, roadmap graphs, robot motion planning, and overall, as long as the lazy or the estimated edge weight function is less than the actual, so kind of similar to a heuristic function, it will always find the optimal path. And there are significant reductions in edge evaluations. So this table is a little confusing, but basically along the top, the first E, F, R, A, and B columns are all the selectors I mentioned at the start that kind of have a already existing algorithm like A star. And then W and P are the new novel ones proposed in this paper. The lines, so like PartCon, unit square, arm plan, those lines all have the number of edges evaluated. And can see that for P, pretty much P always evaluates the least number of edges. That's why it's in bold. So that one does really good. But the major thing here that might be a bit of a drawback to this paper or this proposal is the actual time to evaluate edges, or to actually run this like function to select edges to figure out which ones to evaluate. So the lines below, the line that says online for each of these tests, that's how long the algorithm took to run overall. And there's only one instance where it's shorter. I think that's yeah, ARM plan, the first ARM plan. So that has a runtime of 5.80 seconds, which is all the way to the right for P, which is not much shorter than the 5.9 seconds for the next highest up, which is F on that line. And then all the other ones actually take longer than the shortest other one. So this algorithm has to be like used in a very specific use case. We can see that for ARM planning, it might be good in order to reduce overall time. But in general, the actual selecting edges to evaluate does take a decent amount of time, and that can lead to less overall improvement on runtime, even if it does evaluate less edges overall. And that brings me to the related work.
I mean, this algorithm basically has the same intention as traditional algorithms like A star, since you're trying to reduce the number of edge evaluations. But the only difference is in A star, you're directly computing the true cost upfront. Whereas for lazy SP, you wait until it's absolutely required and you use the provisional weights most of the time, which kind of saves up on a lot of computational cost. And as discussed previously, the lazy SP expand is edge equivalent to A star, and lazy SP forward is edge equivalent to lazy weighted A star. So it's basically doing the same thing as most of these traditional algorithms, except it uses these estimator functions and edge selectors to cut down on unnecessary edge evaluation computational costs. But there are limitations with this particular algorithm in the sense that determining the edge selector itself is a complex process. And secondly, if the edge selector use is not optimal, then it kind of ruins the entire algorithm. Secondly, the paper also mentions adaptive selector strategies as, future work, so that the edge selectors get modified every single time you're evaluating these edges to increase performance. And it also mentions that there should be more future research on a theoretical model to predict selector performance to determine what is an ideal edge selector. Another issue with edge selectors like weight sampler is basically that these edge selectors use probabilistic techniques to determine which edges to find the true cost of. And in some cases, like in the ARM planning domain, where there are a lot of edge dependencies, using these techniques are a bit inefficient, and this is kind of where these edge selectors fail. No.
Sure. I'll be going over the appreciation. So we think like the paper does really like bring up a novel approach to like evaluating edge. So like you can like design your own edge selector and could make it more efficient, like when you combine like with domain specific knowledge. And it contributes to the efficiency and effectiveness in path planning process. And I think it does like very good job at like explaining like the step-by-step proof of like the optimality and the completeness of the lazy shortest path. And then I think it also does really good job at explaining the intuition behind why they select the partition function selector and sampling weight selector. And also, I think the visualization provides like a clear picture of like how the algorithm works, especially like for each of the edge selector. Then for the follow-up work, I think there's like a possible option like for machine learning techniques for like adaptive selector choice. And I think just a few years later, one of the author, Siddhartha Suri, sorry if I mispronounce his name, also co-author like the general lazy search for robot motion planning, interleaving search, and edge evaluation via event-based toggles.
He's a professor here.
Yeah, he is. Yeah. I think he does like publish a lot of like papers on edge evaluation. And I think the general lazy search so the general lazy search approach is that like they realize you need to like both balance out the search planning, the search so the graph search planning, and the also the edge evaluation to like overall like reduce the runtime. And the next paper is the lazy lifelong planning for efficient replanning in graph with expensive edge evaluation. It's also like one of the co-authors is also the same author. So I think in that paper they used the two different approach, like combine like a effective path planning. Essentially it combines the first which is general lazy search and long-term per path planning A star. I think that's pretty much for the follow-up work.
That's it. Thank you for listening.
Thank you. We'll have our last lecture on Wednesday. Let's see that. Yes.